Greetings. Certain types of problems out of antiquity have some very interesting facets to them that we don't often think about. I want to show you one of them. It deals with right triangle. Suppose I have any right triangle you wish to draw. A, B, C, right angle at C. Now, what I want to do is I'm going to come over here and I'm going to put in another segment. From C to the segment AB, I'm going to draw a perpendicular. And this is not a construction that should cause you any problems. That is quite simple, not hard to do. And we'll call this point D. Now the question is, what does all of that have to do with solving some very interesting equations? Well, let's take a look for a moment at a couple of interesting facets. Let's start with the original triangle. Triangle ABC. Now, this is going to be a discussion all about similar triangles. So let's note A to B is the hypotenuse of this triangle, and then B to C is the longer of the two sides. So all the triangles I want to name up here, I need to keep that in mind. I think, since this is a right triangle, maybe it's similar to the one above. But we have to name the hypotenuse first, so that's going to be C to B, and then from B down to D, because that's the longer of the two sides. Now let's look at the last right triangle, this one, and we want to go A to C, and then from C on to D. Now the question is, are these three triangles similar to one another? They are if their angles are actually equal to one another. Now we know by axiom 4 that all right angles are equal, so that's good to know. Now let's take a look at a couple of other angles we know. We also know by Euclid's fifth postulate that every triangle in Euclidean geometry adds up to precisely 180 degrees. So if I know two angles in a triangle, I actually know the third. So I don't have to show all three angles being equal to one another. I just need to show that 2 from the first matches 2 to the second, and 2 from the second will match 2 to the third. Okay, so let's try this out now. So look at the first triangle, the big triangle, and we know that the big triangle contains an angle called ABC that is not a right angle. But notice angle ABC is exactly the same angle as CBD. These angles are in fact equal to one another. And because the other angle in this triangle is a right angle, and there's a right angle in this one, I got all three angles. So 1 is similar to number 2. Now the question is, what can I do? Well, let's take another look. Let's go to the small triangle now. Now, the small triangle doesn't say anything about this angle up here, so I'm going to leave it alone. But go back to the big triangle for a minute. We know we have angle BAC. Well, BAC is hypotenuse short leg. So look at this guy right here, and we have hypotenuse short leg CAD. But notice D could be extended out to B, and all of a sudden, I've named the same angle from just two different directions. It's equal. So that means that number 1 is similar to number 2, which is similar to number 3. Therefore, 2 and 3 must be similar. Now, with that being the case, we now know certain ratios must be true. Let's watch what ratios I'm talking about. Let's take the sides of these triangles, and I'm going to take certain sides to really help me out. So I'm going to take, and I would know that, let's say, the hypotenuse of the big triangle, A to B, is to the long side, B to C, as hypotenuse of this triangle, B to C, is to, and what did I do? B to C, which was long side, B to D. Interesting, but the interesting part about it is I have BC in two spots. That means that AB times BD must be equal to BC squared. That's interesting, but not as interesting as I want to get. Here's the one I'm really after. Let's actually talk about this length, X, and this length called Y. And let's see what we come up with here. Is there something that we can say about these? And I want to talk about H, the length of the hypotenuse. Well, in this case, I've got two triangles, and I've got some different pieces. So let's take a look at this triangle up here. Long side to short side, X is to H. As long side, H is to short side, Y. Now, cross multiply. X times Y is equal to H squared. Now this is actually the finding we're after. We know that these two numbers, when multiplied together, is equal to a square. What square? The square I could build on H. And this is a very interesting finding because this is actually referred to as the geometric mean. The geometric mean of two numbers, X and Y, is said to be the number that you square that gives you the product of X and Y, and that's what we just found. So this very simple construction shows us the geometric mean of two numbers. And you may ask yourself, well, what's all of this got to do with anything? Well, it's one way that we can think about in Greek geometry to actually look at how we solve certain types of problems. This little problem right here is interesting because remember, for the Greeks, they didn't really think of X times Y. They would swing Y around this distance, and they, permit me to get a new color, they would talk about this rectangle right here is equal to this square. And this is the method for going from and showing how you can square any rectangle, because that's what they said they've just done. They squared a rectangle, meaning that they built a square with exactly the same area as a given rectangle. And by the way, this diagram is fascinating because guess what it shows you? Take this little novelty right here. X times Y is H squared. Take the square root of both sides. So the square root of X times Y is H. Let one of these two numbers be equal to 1, whether it be X or Y. And if you do that, you now have a method for how to construct the square root of a number. And that's a methodology we learn in geometry. How do you find the square root of a number? You have to know how to find the geometric mean, which means you know how to square a rectangle, which means, hey, if I say this is length 1, I make this length however many copies of 1 I need, I make a right triangle out of it, and then I know how to get the square root. The Greeks, in doing one problem, would try to solve a whole lot of information out of it. And one simple proposition can be interpreted numerous ways. I hope this helps.